Earth wears its history in scars, vast, ancient craters formed by cosmic collisions. These impact sites, sometimes hidden beneath forests or oceans, tell stories of asteroid strikes that reshaped continents, altered climates, and in some cases, rewrote the rules of life on our planet. But how do we know a crater came from the sky and not from volcanic activity? How can shattered rocks and buried rings reveal events from billions of years ago? In this documentary, we'll travel through deep time and across 5 continents to explore 20 of Earth's most remarkable impact craters. Some are massive structures like VREDEFORT or Chicxulub, tied to extinction events or deep geological upheaval. Others, like DHALA or FOELSCHE, are subtle, mysterious, and still being decoded. You'll see how scientists use shock features, isotopic dating, and satellite imagery to unravel the secrets of these ancient impacts. And you'll discover how they've influenced everything from mineral wealth to climate shifts, even the story of life itself. These aren't just holes in the ground. They're portals to Earth's most dramatic chapters. Let's begin. The MIRALGA impact structure, nestled in the Pilbara region of Western Australia, is one of Earth's oldest known impact remnants, or so scientists once believed. For years, it was thought to have formed around 3.47 billion years ago and measured more than 100 kilometers across. But as research techniques improved, that narrative changed dramatically. The key to this revision lies in a feature called shatter cones, distinctive cone-shaped fractures that only form under the intense pressure of an extraterrestrial impact. At MIRALGA, these structures are found across a 6.5 kilometer area. That suggests the actual crater size is closer to 16 kilometers, much smaller than originally proposed. Even more surprising, the rocks containing these shatter cones are younger than 2.7 billion years. This means the impact must have occurred after that time, not at 3.47 billion years as previously thought. It's a striking example of how impact ages can be misinterpreted without precise geochronology. MIRALGA's story highlights just how difficult it is to piece together Earth's ancient impact record. The evidence is often fragmentary, altered by tectonics or erosion. But even with these challenges, MIRALGA remains a valuable clue in understanding how frequent and powerful these early impacts really were. In the heart of Western Australia lies the YARRABUBBA impact structure, the oldest confirmed impact crater on Earth. For decades, it remained a geological curiosity without a precise age. That changed when scientists analysed tiny mineral grains of zircon and monazite, subjected to intense pressure and heat during the impact. Using uranium-lead dating, they pinpointed the age at 2.229 billion years. This makes YARRABUBBA the most ancient verified impact site known to science. The original crater, once about 70 kilometers wide, has since been heavily eroded. Today, only a faint 20-kilometer wide remnant remains. What makes YARRABUBBA truly fascinating is its timing. The impact occurred during a period when Earth may have been covered in continental glaciers. A modelling study proposed that such an event, a 70-kilometer crater forming in ice-covered terrain, could vaporize massive volumes of water and inject steam into the atmosphere, potentially influencing global climate. In other words, the YARRABUBBA impact might not just be the oldest we've found, it could also have helped bring a glacial episode to an end. It's a powerful reminder of how impacts don't just scar the crust, but can ripple through Earth's atmosphere and climate systems for millions of years. Next, we journey to southern Africa, where the VREDEFORT crater looms as the largest confirmed impact structure on Earth. Around 2 billion years ago, a massive asteroid, estimated at 10 kilometers in diameter, collided with what is now South Africa, releasing energy equivalent to billions of nuclear bombs. The impact was so powerful that it carved a crater 40 kilometers deep and more than 100 kilometers wide. Over time, the ground rebounded and collapsed, expanding the crater to an astonishing 180 to 300 kilometers in diameter. Today, this ancient scar is known as the VREDEFORT Dome, a multi-ringed geological feature recognized as a UNESCO World Heritage Site. What's remarkable about VREDEFORT is not just its scale, but the insight it provides into Earth's deep crust. The impact exposed rocks that once lay 25 kilometers below the surface, allowing geologists to study formations normally hidden far underground. VREDEFORT isn't just a record of planetary violence, it's also a geological gold mine. Its central uplift, roughly 90 kilometers wide, preserves a time capsule of the early Earth, revealing clues about crust formation, rock deformation, and planetary structure. It's the titanic footprint of an impact that forever reshaped the face of a continent. In Ontario, Canada, lies the Sudbury Basin, one of the most scientifically and economically significant impact structures on Earth. Around 1.8 billion years ago, an asteroid or comet slammed into the Canadian Shield, creating a crater estimated at over 200 kilometers in diameter. Though tectonic forces have since distorted its shape into an elliptical basin, Sudbury's origins remain unmistakable. The collision released enormous heat, melting the surrounding crust and forming a vast magma sheet rich in metals. As this molten mixture cooled, it crystallized into ore bodies containing nickel, copper, platinum, and other valuable elements. Today, the Sudbury Basin is one of the world's most productive mining regions, but its importance goes far beyond economics. It's a prime example of how impacts can generate long-term geological and industrial consequences. The mineral wealth left behind isn't just a byproduct. It's a direct result of the energy released during the impact. Sudbury also offers clues about Earth's ancient surface. The event punctuated a critical period in planetary evolution and may have even influenced the composition of Earth's early atmosphere. It reminds us that extraterrestrial collisions don't just scar the planet, they can also seed it with the building blocks of modern civilization. Hidden in the remote deserts of Western Australia lies the Shoemaker impact structure, once known as the Teague Ring. Spanning roughly 30 kilometers in diameter, this eroded crater is named after legendary planetary geologist Eugene Shoemaker, whose work helped pioneer the field of impact science. Unlike fresh craters with sharp rims and obvious features, Shoemaker is subtle. Its presence is revealed through warped sedimentary layers and a faint, concentric ring pattern visible in satellite imagery. These clues point to a complex geological past shaped by immense forces. Determining the crater's exact age has proven difficult. Estimates place its formation somewhere between 1 billion and 600 million years ago. That wide range highlights the challenges of dating ancient structures that have been weathered, uplifted, and partially erased over time. What makes Shoemaker scientifically valuable isn't just its size, it's how it illustrates the process of crustal deformation. The impact disturbed sedimentary strata, bending them into ring-like formations that geologists still study today to understand how impacts shape layered terrains. Though less visually dramatic than younger craters, Shoemaker stands as a quiet monument to Earth's long history of cosmic bombardment, a subtle reminder that even the most weathered scars still have stories to tell. In the heart of Finland lies the QUEBEC impact structure, a quiet but significant remnant from the Mesoproterozoic era. For years, it puzzled geologists who suspected an ancient impact but lacked solid evidence. That changed with the discovery of pseudo-tachylitic breccia, a rock formed by the intense friction of an impact event. Using advanced 40R39R dating techniques, scientists determined the impact occurred approximately 1.14 billion years ago. The crater itself is thought to have originally spanned up to 30 kilometers, though erosion has softened its features and scattered its geological signals. KEURUSSELKÄ's significance lies not in its size, but in its survival. Despite more than 1 billion years of tectonic activity, glaciation, and surface weathering, signs of the impact still remain. These include shatter cones, breccias, and shocked minerals, all classic hallmarks of an extraterrestrial collision. The structure also serves as a case study in persistence. Many craters this old have vanished without a trace. But in KEURUSSELKÄ, scientists found a geologic time capsule that helps reconstruct the conditions of Earth's crust during the Mesoproterozoic, a period with few preserved impact records. It reminds us that even subtle features can preserve profound stories about Earth's violent past. In central India, surrounded by ancient granite hills, lies the DHALA impact structure, a lesser-known but geologically intriguing site. At roughly 11 kilometers in diameter, DHALA may not rival Earth's largest craters in size, but its complexity makes it one of the most enigmatic impact sites on the subcontinent. The crater formed in Paleoproterozoic basement rocks, estimated to be around 2.5 billion years old. Yet determining the exact age of the impact itself is far more challenging. Scientists have dated zircon grains from melt rocks at 2,563 and 2,553 million years, consistent with the host rocks. But additional zircon overgrowths show thermal disturbances at 1 billion and 530 million years ago, likely caused by later metamorphic events. These multiple age signatures complicate the crater's story. Is DHALA as old as the host rock? Or did later tectonic activity reset its geochronology? Despite the uncertainty, DHALA offers valuable insight. It's one of the rare impact structures found within high-grade metamorphic terrain, making it a prime target for studying how impact processes interact with deep crustal rocks. Its location, age complexity, and geological setting make DHALA a fascinating puzzle, one still waiting to be fully solved. Straddling the border between Idaho and Montana in the United States lies the BEAVERHEAD impact structure, a massive ancient scar in the heart of the Rocky Mountains. Though heavily eroded, this crater is estimated to be about 60 kilometers in diameter, placing it among the largest known impact sites in North America. The primary evidence for the impact comes from shatter cones, rare conical fractures formed only under extreme shock pressures. These features, along with disrupted bedrock and subtle geophysical anomalies, helped geologists identify BEAVERHEAD as a deeply eroded impact site. Dating the structure has proven difficult, but current estimates suggest an age of around 600 million years during the Neoproterozoic era. That places the impact in a time of dramatic global change, possibly even during one of Earth's hypothesized snowball Earth glaciations, though no direct connection has been established. What makes BEAVERHEAD notable is how little remains of such a large event. Time, tectonics, and erosion have worn away its crater walls and central features, leaving only traces for geologists to piece together. It's a reminder that some of Earth's most colossal events have left only faint fingerprints, clues hiding in plain sight within ancient mountain ranges. In the Gawler Ranges of South Australia lies one of the most dramatic impact structures from the late Precambrian, the ACRAMAN crater. Estimated to be around 590 million years old, it dates to the Ediacaran period, a time when multicellular life was beginning to emerge on Earth. The impact was colossal. The structure features a central uplift about 40 kilometers wide and an estimated outer rim stretching 85 to 90 kilometers. Some disturbed rock extends as far as 150 kilometers, indicating a blast powerful enough to reshape the surrounding terrain on a continental scale. What makes ACRAMAN particularly significant is the discovery of its ejecta, pulverized rock and debris from the impact, preserved in sediment layers hundreds of kilometers away. These ejecta serve as a clear geologic marker, helping scientists date the impact and correlate it across vast distances. There's also a tantalizing possibility. The impact may have affected early life. Some researchers suggest the ACRAMAN event triggered environmental shifts that influenced the course of Ediacaran evolution. While the link remains debated, the timing is compelling. ACRAMAN is a textbook example of how a single cosmic event can echo across both space and time, leaving imprints in stone and perhaps in biology. Tucked away in Australia's Northern Territory lies the FOELSCHE crater, a modest, heavily eroded impact structure with a mysterious past. Measuring only about 6 kilometers in diameter, it's one of the smaller craters in this documentary, but its scientific value remains significant. FOELSCHE is thought to be older than 545 million years, placing it somewhere in the late Precambrian or possibly earlier. However, the precise age remains uncertain due to limited exposure and the effects of erosion over hundreds of millions of years. What makes FOELSCHE notable is the clear evidence of shock metamorphism in its rocks. Minerals within the structure display deformation features consistent with a high-energy impact. Yet, like many small and ancient craters, much of its topography has been worn away by weathering and tectonic processes. Despite its subtle presence, FOELSCHE serves as a critical data point in Earth's impact record. It reminds researchers that not all impact structures are dramatic or obvious. Some lie nearly forgotten, hidden within landscapes that seem otherwise unremarkable. The crater stands as a quiet testament to Earth's vulnerability, offering a glimpse into the countless impacts that have shaped our planet, even when the evidence is nearly erased. In the remote forests of northern Quebec, two strikingly circular lakes, Clearwater East and Clearwater West, have long captured the attention of geologists and astronauts alike. At first glance, they appear to be twin impact craters formed by a double asteroid strike. But deeper investigation has revealed a more complex history. Clearwater West is the larger and younger of the two. Measuring about 36 kilometers in diameter, it features a central ring of islands, classic evidence of a complex impact crater. Radiometric dating places its age at around 286 million years. Clearwater East, on the other hand, is smaller at 26 kilometers and more deeply buried beneath sediments. Surprisingly, it is significantly older, dated to between 460 and 470 million years ago. This time gap confirms that the craters were formed by two entirely separate impact events, nearly 200 million years apart. The Clearwater craters are a rare opportunity to study impact structures in close proximity with contrasting preservation states and geological contexts. They offer insight into how different conditions, from erosion to glaciation, shape crater evolution over time. Together, these lakes stand as beautiful and scientifically rich reminders of Earth's long history of cosmic bombardment. Located in Ontario, Canada, the Brent crater is a smaller and lesser-known impact structure, but it offers valuable insight into planetary geology. Estimated at around 3.8 kilometers in diameter, it's modest in size compared to the giants like VREDEFORT or SUDBURY, yet it provides a surprisingly rich scientific record. The crater is nestled within the rugged landscape of Algonquin Provincial Park. Although erosion has softened its features, the circular outline remains distinct. Geological surveys have confirmed its impact origin through the presence of shatter cones and deformed quartz grains, key indicators of high-pressure shock. Unlike many craters of its size, Brent has been relatively well studied. It's believed to have formed during the early Paleozoic, though the exact age is still debated. The impactor was likely a chondritic asteroid, based on geochemical traces found in the region. Brent's real value lies in its accessibility and preservation. It provides a field site where researchers can examine impact structures without the complications of deep burial or heavy metamorphism. In that sense, it serves as a geological laboratory, a small but clear window into the mechanics of crater formation. Sometimes, even a minor scar can reveal major secrets about Earth's past. Along the banks of the St. Lawrence River in Quebec lies the Charlevoix impact structure, a dramatic and complex scar partially hidden by mountainous terrain. Estimated to be about 54 kilometers in diameter, the crater is one of Canada's most striking examples of a large impact structure integrated into a modern landscape. Charlevoix was formed around 450 million years ago, likely during the late Ordovician or early Silurian period. The impact reshaped the region, fracturing rocks and altering geological formations across a wide area. Evidence for the impact includes shatter cones, planar deformation features in quartz, and a distinct circular pattern in local topography. What sets Charlevoix apart is its human connection. Unlike many remote craters, it's home to towns, farms, and roads, a living example of how life has reclaimed an ancient cataclysm. The structure's rugged beauty attracts tourists and geologists alike, offering a rare blend of accessibility and scientific importance. Charlevoix reminds us that impact events don't always leave barren wastelands. Over time, nature and civilization can flourish in these once devastated zones. Beneath the rolling hills and scenic vistas lies a violent story told in fractured stone and shocked minerals. Deep in the remote wilderness of northern Saskatchewan lies the CARSWELL impact structure, a circular anomaly carved into the Canadian Shield. Measuring about 39 kilometers in diameter, it's a relatively young crater formed approximately 115 million years ago during the early Cretaceous period. The impact created a complex structure with uplifted central rocks and deformed surrounding layers. Over time, glacial activity and erosion softened its features, but the circular shape remains visible in topographic maps and satellite imagery. What makes CARSWELL particularly significant is its economic and scientific value. The crater is home to the Cluff Lake uranium mine, which operated for over 2 decades and produced millions of pounds of uranium. The impact not only fractured the crust, but also influenced fluid flow, which contributed to the concentration of uranium deposits. CARSWELL provides a rare opportunity to study how impact structures can influence ore formation and hydrothermal systems. It stands as an example of how destructive cosmic events can, over time, become engines of resource abundance. Today, the site is largely abandoned, but its legacy continues, not only as a geological feature, but as a reminder of how Earth's past violence can shape its future potential. In central Sweden lies the SILJAN Ring, Europe's largest confirmed impact crater and a geological landmark shaped by one of the most powerful events in the continent's history. Formed around 377 million years ago during the Devonian period, the original crater is estimated to have been approximately 52 kilometers in diameter. The structure features a distinctive circular depression surrounded by faulted and folded rocks. A central uplift marks the site of the impact's rebound, while ring dikes and annular fractures illustrate the immense forces unleashed during the collision. SILJAN has attracted scientists for generations, not just for its structure, but for its potential clues about Earth's history. Its age coincides with the late Devonian extinction, a period of major biodiversity loss, prompting speculation that the impact may have played a role. Though no definitive causal link has been established, the timing is intriguing. Today, the SILJAN area is known for its scenic lakes and geothermal energy potential. It represents a successful fusion of natural beauty and scientific importance, offering a well-preserved window into Earth's dynamic past. The SILJAN ring reminds us that even in Europe's quiet heartland, the planet bears the marks of ancient violence from beyond the skies. In the wilderness of Quebec, Canada, lies one of Earth's most iconic impact structures, the Manicouagan crater, often called the Eye of Quebec. With a central ring about 70 kilometers in diameter, the full impact structure is estimated to have originally spanned roughly 100 kilometers. Formed around 212 million years ago, during the late Triassic period, the Manicouagan impact is believed to have been caused by a 5-kilometer-wide asteroid. The collision vaporized rock, released unimaginable energy, and permanently altered the landscape. Today, the crater is partially filled by the Manicouagan Reservoir, a ring-shaped lake created by hydroelectric dams. Its distinct circular form is clearly visible from space, a vivid reminder of the event's magnitude. What makes Manicouagan particularly valuable is its exceptional state of preservation. Despite its age, the structure retains well-defined concentric rings, a central uplift, and shock metamorphic features that allow scientists to study crater formation and erosion in detail. There is also speculation that the impact may be linked to one of several extinction pulses in the late Triassic, although the evidence remains inconclusive. Regardless, Manicouagan remains one of the best preserved large impact structures on Earth, a cosmic scar visible even from orbit. In the Volga region of Western Russia lies the PUCHEZH-KATUNKI impact structure, a buried and eroded crater that offers a rare glimpse into Jurassic Age cosmic events. Although its surface expression is faint, geophysical studies and drilling have confirmed its origin as a complex impact site. The structure measures approximately 40 kilometers in diameter. For years its age was uncertain, but recent 40R39. Our radiometric dating of impact melt rocks yielded a precise age of 195.9 million years, right at the transition from the Triassic to the Jurassic. This timing is scientifically valuable. While PUCHEZH-KATUNKI is not linked to any known mass extinction, its well-preserved subsurface features provide a detailed case study of how medium-sized impacts deform the crust and create complex central uplifts, ring faults, and fractured rock zones. Much of the structure is buried beneath sediment, limiting surface exploration. But core samples have revealed shocked quartz, melt breccias, and impact glass, key signatures of a high-energy collision. PUCHEZH-KATUNKI reminds us that many significant impacts lie hidden from view, preserved beneath layers of time. And with every new drill core, this Jurassic crater continues to teach us about Earth's deep time interactions with the cosmos. Beneath the sands of South Africa's Kalahari Desert lies the elusive MOROKWENG crater, a massive buried impact structure that remains shrouded in mystery. Unlike surface-visible craters, MOROKWENG is hidden beneath layers of sediment and rock, detectable only through geophysical anomalies and drilling. Estimates suggest the crater could be up to 70 kilometers in diameter, placing it among the larger confirmed impact sites on Earth. Radiometric dating of impact melt rocks recovered from drill cores suggests an age of about 145 million years, near the boundary between the Jurassic and Cretaceous periods. What makes MOROKWENG particularly intriguing is the discovery of a metallic object in the drill core, possibly a fragment of the original asteroid. If confirmed, it would be one of the rare examples of preserved impactor material from a large-scale event, offering unprecedented insight into the composition of celestial bodies that have collided with Earth. Despite its scale, MOROKWENG remains poorly understood due to its buried nature. Its geophysical signature, age, and potential asteroid fragment make it a prime target for future research. This hidden giant serves as a reminder: some of Earth's most powerful impacts are not visible at all, only detectable by probing deep beneath the surface. few impact craters are as famous, or as consequential, as Chicxulub. Located beneath the Yucatan Peninsula in Mexico, this massive structure marks the site of the asteroid impact that likely triggered the mass extinction that ended the age of dinosaurs. The crater spans approximately 180 kilometers in diameter, making it one of the largest confirmed impact sites on Earth. It formed about 66 million years ago, when a 10-kilometer-wide asteroid struck Earth with a force equivalent to billions of atomic bombs. The effects were catastrophic: global wildfires, mega tsunamis, and a nuclear winter caused by dust and aerosols blocking sunlight. This rapid environmental collapse led to the extinction of roughly 75% of all species on Earth, including nearly all dinosaurs. Chicxulub is exceptionally well studied. Drilling projects have revealed shocked quartz, melt rock, and a distinctive peak ring structure, evidence of the immense energy released during the impact. The event left a clear boundary in the geologic record known as the KPG boundary, visible worldwide. Chicxulub is more than a crater. It's a planetary turning point. It reshaped ecosystems, rewrote evolutionary history, and paved the way for mammals, and eventually humans, to rise in a post-dinosaur world. From the weathered rings of MIRALGA to the dramatic depths of Chicxulub, Earth's impact craters tell a story written in stone. A story of cataclysm and resilience, destruction and renewal. These 20 structures represent more than just scars from the past. They are planetary time capsules, capturing the moment when the cosmos collided with Earth. Some, like Sudbury and CARSWELL, changed geology and economics. Others, like YARRABUBBA and ACRAMAN, may have altered climate or life itself. And craters like VREDEFORT and Chicxulub remind us that even the most advanced ecosystems can be wiped away in an instant. Yet these impacts also bring knowledge. They reveal how Earth responds to extreme energy, how minerals form under intense pressure, and how life over time finds a way to return. They challenge scientists to look deeper, drill further, and rethink planetary history. Perhaps most importantly, they remind us that Earth is not isolated. We are part of a solar system, vulnerable to cosmic events beyond our control. Understanding these ancient impacts helps us prepare for future threats and appreciate the fragile beauty of our world. If you found this journey through deep time fascinating, consider liking the video and subscribing for more.